All right, good evening, and thank you for joining us tonight at this, the 40th annual Michelson Memorial Lecture. After a 39-year run of annual Michelson Lectures, we were unable to host one at this time last year for obvious reasons, but we're back and we're ready to begin a brand new consecutive streak. This annual lecture is one of the highlights of our academic year, and it affords us a chance to hear from some of the world's most renowned scholars who, like Albert Michelson himself, make significant and long-lasting contributions to their fields. Tonight's speaker, Dr. Marcia McNutt, is no exception, and I know you will very much enjoy this evening with her. Before we introduce our speaker, though, I first would like to thank the great class of 1969 for their most generous sponsorship of this lecture this year and every year. May I please ask the members of the class of '69 to please stand and let us properly thank you. Without your support, there would be no Michelson Lecture, so thank you very, very much. As is our custom at the start of the Michelson Lecture, I'd like to take a few minutes to tell you, especially you midshipmen, a little bit about Albert Michelson, the man in whose name we host this lecture series. Albert A. Michelson is a Naval Academy graduate from the great class of 1873. Albert was born in Strelno, Prussia in December of 1852, just 7 years after the establishment of the Naval School in Annapolis, as that's what they called this place at the time. And like so many others of that era, Michelson's family emigrated to the United States when he was only 2. The Michelsons settled in Nevada, but then eventually moved to San Francisco, where Albert received his early education in the public school system, graduating from high school in 1869. So he too is a member of the class of 1869 in that case. This was shortly after the end of the Civil War, and he then received an appointment from President Grant to attend the Naval Academy. After graduation, he was an ensign in 1873, and he served on a 2-year cruise in the West Indies. And then, like many officers do today, he returned to the Academy as a lieutenant to teach. In Michelson's case, he returned as an instructor in both physics and chemistry. Like many officers even today, he served at the Academy for only a short period of time, 4 years in his case, leaving in 1879 for his next tour. But those 4 years at the Naval Academy have left a very large and lasting impact. During his career, Michelson touched on many aspects of physics, but his specialty was optics. He performed early measurements of the speed of light with amazing precision. In fact, he was the first person in the world to accurately measure the speed of light, and he did that here in Annapolis. During his time here as a lieutenant, he performed his famous speed of light experiments along the old seawall. As you might know, the location of the seawall at that time was where the 2 science buildings, Michelson and Chauvenet, now stand. Today, the location of his experiments are marked by aluminum discs embedded in the terrace between those 2 buildings. Perhaps you've seen those discs in the terrace as you walk between the buildings, but if not, I encourage you to notice them the next time you walk by there. It was in 1881, though, after he left here, when he performed the experiments for which he is most famous. At what is now known as Case Western Reserve University in Cleveland, Ohio, and with his colleague Edward Morley, he invented a device called the interferometer, a device designed for the purpose of discovering the effect of the Earth's motion on the observed velocity of light. In cooperation with Morley and using the interferometer, they showed that light travels at a constant speed in all inertial systems of reference. But here's the most interesting part. Physics theories of the late 19th century postulated that, just as water waves must have a medium in which they move, and audible sound waves require a medium to move through as well, so too, then, must light waves require a medium. And they called that medium the luminiferous ether. That was the widely held belief in the day. And because light can travel through a vacuum, it was assumed that the vacuum must contain that medium, the so-called ether. So the Michelson-Morley experiment was designed to confirm the existence of the ether. And you know what happened, right? What exactly does a vacuum contain? Nothing. No ether at all. That is, the experiment failed to prove the existence of the ether that so many were convinced had to exist. After all their thought and preparation, that experiment turned out to be the most famous failed experiment to date. Instead of providing insight into the properties of the ether, Michelson and Morley provided what is generally considered to be the first strong evidence against the theory of a luminiferous ether. This then triggered a revolution in physics and a new way of thinking about science and energy. This is the work for which Albert Michelson was awarded the 1907 Nobel Prize in Physics. For our purposes here at the Naval Academy, there is perhaps another legacy worth noting. Michelson's story is not only one of scientific genius, but also of courage. Courage to question the conventional wisdom and to stand by principles in the face of an avalanche of contrary opinion. This tale is often repeated in the history of science, to stand against an overwhelming majority of contrary opinion, and to do so with objective evidence and the knowledge that you're right. And just to reassure you budding scientists in the room that there's still room for such courage in your field, even Michelson was wrong about a few things. And as an example, here is what Albert Michelson himself had to say in 1903, and this is a quote. "The most important fundamental laws and facts of physical science have all been discovered. And these are now so firmly established that the possibility of their ever being supplemented by new discoveries is exceedingly remote." So there you go, no one's perfect. That's just a little bit about one of our most extraordinary graduates, Albert Michelson. And now I would like to invite Captain Eric Wolper, the Dean of the School of Math and Science, to please introduce our tonight's speaker.
All right, it is a great honor and pleasure to introduce our guest Michelson lecturer, Dr. Marcia McNutt. Dr. McNutt's achievements are too voluminous and certainly too impressive to be done justice within the confines of my introduction. So my goal, instead of summarizing her very impressive career, is instead to get you as excited about her presentation as I am. Several months ago, we initiated the effort to invite a speaker for this evening, and Dr. McNutt was our stretch goal, our moonshot, if you will. We knew she would be extraordinary, but we were uncertain if she would say yes. So Dr. McNutt, thank you very much for saying yes. Dr. McNutt is the 22nd president of the National Academy of Sciences. Notably, Albert Michelson was a previous president from 1923 to 1927. To give the audience a sense of how lucky we are to have her with us this evening, she just finished hosting the 158th annual meeting of the National Academy of Sciences this past Saturday and Sunday in Washington, D.C. She and the Academy then co-hosted the Nobel Prize Summit the past 3 days, including today. This summit included scores of Nobel laureates and others exploring questions about how humankind's future on Earth will be achieved and shaped. She completed her hosting duties at 1600 today and was at the Naval Academy Club by 1730. I have no idea how you managed that time distance problem, but it's worth mentioning that the previous speaker in this series, Dr. Kip Thorne, explained time travel to us in the context of black holes. Dr. McNutt's career started off with a bang, literally, already in graduate school when she trained in underwater demolition with Navy SEALs, and I learned a few minutes ago that she also was an extra in the movie The Attack of the Killer Tomatoes. Now, as a submariner, I am grateful that she shifted from blowing things up underwater to focusing on the composition and bathymetry of the seafloor in the South Pacific. You can see on the slide an image of the USS San Francisco in January 2005 after colliding with an underwater seamount that was not indicated on the navigational chart that the crew was using. Gaining better understanding of the Earth's seafloor is important for all of humanity, and particularly important for submariners like me. However, I'd like to close my introduction by summarizing our explanation to Dr. McNutt in our invitation to her several months ago why we think she should come speak to the midshipmen at the Naval Academy. We said, "Your career in science closely parallels the journey the midshipmen will embark upon after graduation. You developed core competence within your discipline through scholarly research, relentlessly chasing hard problems in often challenging conditions at sea. You led organizations of increasing size and complexity, and you have maintained your own unique passions throughout this journey. From rodeos," she competes in barrel racing, to camping trips, your passion for the outdoors remains intact, and you've found ways to feed this passion outside of work, which likely has helped you retain balance and perspective. Simply put, the midshipmen will be able to relate to you and see themselves in you. So ladies and gentlemen, please join me in welcoming Dr. Marcia McNutt.
So, wow, I was already quite thrilled to be invited to give the Michelson Lecture, but I didn't realize it was that Michelson, the Michelson of Michelson and Morley. I am just beyond thrilled to be standing up here doing what I love to do, which is talk to people about science, but with a lecture named after such a famous physicist. This is truly an honor. Thank you very much. So today, what I thought I'd talk to you about is a topic that is near and dear to my heart, and that is how important science and technology are for strategic advantage. Whether you're in the Navy or the Army or whatever part of uniformed services or even politicians, understanding science and using it to our advantage has been through the history of America a way that we have remained the strong nation that we are. So let me begin by telling you a little bit about the organization I now lead, which is the National Academy of Sciences. As I say on this slide, the National Academy was born in war. And as the story goes, there was the battle of the first two ironclad warships, the Monitor and the Merrimack, the Battle of Hampton Road. And these two warships lodged cannonballs at each other with them just bouncing off the side of the ships because they were ironclad. And they battled to a draw in Chesapeake Bay. Abraham Lincoln, when the word of this great naval battle that ended in a draw reached him in Washington, he decided that he wanted to have the scientists on his side. Congress was going into recess, and as Congress went into recess at midnight, the last moment, when Congress was still in session, he got a bill through creating the National Academy of Sciences, but not as an honorific society, rather as a working group of scientists in service to the nation. Lincoln wanted the scientists on his side, not the Confederate side. So the first job that he gave to the National Academy, you might not be surprised to hear, was how the heck do you navigate with a magnetic compass and iron warship? And so that was the first job of the Academy, to figure out how to do magnetic shielding so that a compass would work on an iron warship. So the next big sort of boost in size and prominence that came to the National Academy was during World War I, otherwise known as the Great War, because of course there was only one at the time, so they couldn't put a one after it. This was an important expansion of the Academy's advising function, because this was the first opportunity to really enlist scientists to help with the war effort. And so actually, one of the first things that the Academy recommended to the nation was that they should officially enlist scientists, but not put them out on the front lines in the trenches, but rather make them work for the government, applying their science for technological advantage. This was also the birth of submarine warfare. The first submarines were used then. And so how do you detect a submarine when they're running silent, running deep? They developed the first operational weather forecasts during World War I. And the Academy also advised on an important problem, the supply of domestic materials for explosives, because that became a supply chain problem. Then came World War II. And no one can doubt but that in World War II, science and technology provided a strategic advantage to the US and to the Allies, and it made a difference in the outcome of the war. Some of the things that the National Academy promoted were new kinds of weaponry, the use of computers, radar, which was being developed just right before the war, new methods of communication, field medical interventions that actually saved numerous lives, and of course, rocketry, and then, of course, the atomic bomb as well. So at this time, the Academy's reputation was cemented as being important to the national effort. However, the message that I want to give you today is that science won't do any good in terms of helping a nation have a strategic advantage if the leaders don't listen to scientists. During World War I, the flu of 1918, the Army came to the Academy and said, we've got all these young men getting sick, some of them dying. What do we do? So the Academy quickly pulled together some experts, and their advice was, not a surprise, you've heard it today, people have to socially distance. If someone gets ill, you have to figure out who they've been in close contact with and get those people quarantined as well. The Army chose to ignore that advice and did nothing to change how troops were quartered and how troops were deployed. In the end, and they did that because they said, well, we're the Army, that's not the way we do things. In the end, the flu affected 20 to 40% of the US troops and produced a higher mortality rate than enemy fire. So I guess what I'd like to say is, how are you midshipmen out here going to become science-savvy officers so that you know how to take advice from scientists and how to apply that science to your situation at hand in order to gain strategic advantage? So what I'd like to do in my lecture today is talk about 4 pieces of advice I have for midshipmen on how to become science-savvy officers. The first is embrace cutting-edge science and technology and keep up. You will never stop learning. You think, oh, I'm going to graduate, I get my degree, I'm done. No, you have to become a continual learner because science and technology is moving so fast that if you don't keep up, you're going to be left behind. Next, know how to assess and mitigate risk. This is an important part of decision making. And establish credibility as a valued member of your team. And I'm going to give you an example of that. And finally, protect your reputation. I don't think people are worrying enough about this today in the age of social media, about how your digital presence can be forever. Okay, so let me move on to the first topic, which is embracing cutting-edge science and technology. And let me tell you a little story from early in my career, which has some connection to that great introduction today. So when I was a graduate student about to defend my thesis, the Navy put up a novel satellite called CSAT. It was the first radar altimeter that was flown in space. The purpose of it had nothing to do with measuring topography or bathymetry on the seafloor, but rather it was to measure the dynamic surface of the ocean caused by tides and currents. So that basically, if the ocean weren't moving at all, the ocean would be an equipotential surface. But once the ocean starts moving, in the Kuroshiro, in the Agulhas, in the Gulf Stream, it creates a topography that's a departure from the equipotential surface. And the purpose of CSAT was to measure precisely currents using the height of sea above the equipotential. I remember distinctly a day when I was at my building at Scripps Institution of Oceanography, when one of the oceanographers came up to me and he said, "You know something, Marcia? You should be interested in this. CSAT is so good that it's actually measuring bumps on the surface of the ocean that are caused by seafloor bathymetry." And I looked at him like, what? How can something deployed from space be measuring something on the bottom of the ocean through an ocean that is basically opaque to the electromagnetic spectrum? But sure enough, I looked into it, and there were distinct elevation of the seafloor above every seamount and underwater volcano and ridge, and there was a depression at the ocean trenches. So a couple years later, in 1983, I was co-author on the first paper to invert that data to recover seafloor bathymetry from space. Now, the way this was done, my contribution to this paper was actually to come up with the spectral filters that you would put the CSAT data through in order to recover bathymetry from the elevation of the ocean. And these filters are very unstable. They blow up at short wavelengths, and they blow up at long wavelengths. But there's a sweet spot for scales between about 15 kilometers and 150 kilometers when you can use this data to actually improve the bathymetric maps that were available at that time. So you have to just assume you have to do a cutoff filter to get rid of short wavelengths that are just going to be noise that will hide the signal. And at long wavelengths, you had to use existing bathymetric charts to recover the base level of the ocean. But from that base level, then, the CSAT data was ideally suited to recover features that were between 15 kilometers and 150 kilometers. So let me show you now a bunch of generations of maps. What I've shown in this panel is ship tracks in this part of the Pacific superimposed on a map of the US, just to show you the scale of this area. And what you can see is down in this area of the South Pacific, here's the Louisville Ridge, the Pacific Antarctic Ridge, Antarctica's down here, that there are whole areas the size of Wyoming where no ship had ever been. So large areas of the seafloor where there had never been an echo sounder, there had never been a multi-beam sounding system over it, where the bathymetry of the ocean was basically unknown. You saw that picture of the San Francisco after it had bashed into an uncharted seamount. It was not a good idea to have such large areas of the ocean completely unmapped. So this little red line, which has come in right here, shows a ship track that I took an oceanographic ship out in 1992. And at that point, the only ship that had ever visited that part of the ocean before me was Captain Cook, and that was in the 18th century. Now, according to Captain Cook, in this area of the ocean, Cook said, oh, it shows it again, okay. Cook said that there was this bathymetric feature called Faber Bank. And Cook had done soundings and marked Favored Bank as a very shallow, planed-off submarine volcano that definitely needed to be avoided. Now, and Favored Bank as a feature was therefore included in subsequent maps by Jebco, the DBDB series, and on NOAA charts. So there was this big feature called Favored Bank. When I analyzed the satellite altimetry for where Favored Bank was, there was nothing. Flat seafloor. CSAT showed absolutely no feature at the location of Favored Bank. But it showed another feature at the same latitude, but 100 nautical miles to the west, that was not on any of the charts, but looked really huge in the satellite data. So as we were running that line west, we went over the purported location of Favored Bank, according to Cook. Flat seafloor, nothing there. But I called up to the bridge and I said, I think Favored Bank is just mislocated. Because, of course, clocks were not really very good at the time of Captain Cook, and that was the only way they determined longitude. So it was very easy to understand that it could be dead on in latitude, but off by a large distance in longitude. So we continued to steam west, and it was late at night. I called up the bridge and I said, according to my analysis of the satellite data, there's a feature up in front of us, and it's really big, so you might want to slow down. So the captain gets on and he says, well, you know, I don't see anything here. There's nothing on my chart. So we go along a little bit more through the night, and I'm watching the sea beam, and I'm seeing the bottom of the ocean start to rise. So I call up to the bridge again, and I said, the seafloor's coming up right where I said this feature was, and it's coming up fast. So the captain sat the seaman up to the flying bridge to keep a lookout. It was a full moon that night, and in the full moon, I hear about 20 minutes later, breakers dead ahead. And I heard the roar of the bow thrusters coming on and the engine screaming as the captain turns to avoid mislocated Favored Bank. So this is a situation where using technology that had never been applied to this purpose before, and in fact wasn't even designed for this purpose, actually probably that night saved our ship from a pretty awful encounter. Today's mapping platforms are, of course, very much more sophisticated. When I was director of the Monterey Bay Aquarium Research Institute, we developed this mapping autonomous underwater vehicle that could do high-resolution bathymetry at the fraction of ship costs. We sent it out to, you could send it out from a ship. It could cover much more distance, and with a fleet of them, you could actually do swath mapping at scales and at resolutions that were not even available before. And this just shows the launch of this. We had to build a special launch system for the heavy seas in the North Pacific, but it was a great workhorse, and we got lots of good data from it. So most of the ocean still remains poorly mapped. I think some of you midshipmen may be too young to remember the search for Malaysian Airlines Flight 370. Went down in the Indian Ocean, all hands on deck, and no one ever found. In fact, they had a difficult time even knowing where to search. And one of the problems in knowing where to search is that the Indian Ocean is so poorly mapped. This was the best map available for the Malaysian Airlines search area, and it was based on satellite altimetry, inversion of satellite altimetry. And here's a quote from Vice Admiral Shin Tani, who said, "Since 1991, we have known more about the topography of Mars than we do about the Earth's seafloor, and oceans certainly have a much more direct impact on our everyday lives than the surface of Mars." So I'm happy to see that there are still continuing advances in mapping. Future mapping capabilities are going to combine sonar with LIDAR and photography to get unprecedented resolution of the seafloor and put these on autonomous vehicles that will be able to do it at a fraction of the cost of surface mapping. So let me change now and talk a little bit about the many reports that the Academy's done on ocean security, and here are some covers for some of them. Some common themes emerge from all of these reports. One is that the Navy and the military needs to collect higher resolution, multidimensional data at high spatial and temporal resolutions, especially in the littoral zone, to constrain high-res models and for timely decision-making. So these kinds of technologies I've been talking about, the LIDAR plus the photography plus the AUVs, are exactly the sort of thing that's going to be necessary to do that. And secondly, to ensure that efforts to enhance environmental information are carried out in a cost-effective manner that maximizes resources. So again, going to autonomous platforms in order to collect more high-res data. But one aspect of oceanography that I think is more future-looking and hasn't been completely taken advantage of is the fact that our situational awareness in the ocean is patterned much the way we probe the terrestrial environment. We've been sort of locked into this trying to adapt land systems and make them work in the ocean. But the ocean is a very different fluid than the atmosphere. It is really a biochemical reactor. The biology is constantly reacting with the chemistry, which is reacting with the physics. And how can we use that to our advantage for situational awareness? For example, how can we use those biochemical reactions to detect events? For example, a natural event that might require reinitializing a model or altering a decision because of something you learn about the environment from measuring those biochemical reactors. Or an anthropogenic disturbance of importance. There may be something that has entered your battle space that you can use the biochemical reactions in order to sense it. So the ocean is filled with microscopic biological sensors. They're sensing, excuse me, the ocean's physics, its chemistry, and biology on a whole variety of scales, from small scales to larger scales. And these microscopic biological sensors concentrate in boundary layers where there are high gradients of energy or food. They have a range of mechanisms for sensing their environment and for communicating with each other. Basic research leads to opportunities to exploit these natural sensors for situational awareness. And here's just one example of that. It's called quorum sensing. How many of you are familiar with quorum sensing? Okay, so quorum sensing is a group behavior that bacteria and other microscopic organisms display when there are enough of the cells in close proximity to trigger it. And these organisms, when there's low cell density, they have very individual behavior. But if they're at high density, they don't act as single organisms. They act as a collective organism. They act as a group. So the question is, how can we understand more about quorum sensing in the ocean? How can we learn the language of quorum sensing and use it to understand what's going on in the ocean, particularly on boundary layers? Okay, so if we could devise a method to turn off quorum sensing, we could be less detectable in the ocean. If we could find other systems that use quorum sensing and produce some easily observed then gene expression and make quorum sensing work in organisms that we prefer to work with. And perhaps we could even enhance the threshold for the quorum response to allow for broader ranges of detection. Right now, quorum sensing, you have to be very close to observe it. But there's always the possibility that it could have larger ranges of detection. So that's just one example of things that are going on in science that could be of interest to the military. So one example that could perhaps be a real-life case of quorum sensing in the ocean is what happens with whale falls. I was telling my company at dinner about how we did a lot of research when I was at the Monterey Bay Aquarium Research Institute on dead whales, usually because someone had a stinky whale on their beach and they wanted us to remove it and sink it. And when a whale dies and it sinks to the bottom of the ocean, it is basically manna from heaven that rains down on the bottom of the ocean. The ocean floor is fairly depleted in organic matter, but suddenly 7 to 15 tons of organic material arrives at the bottom of the starved place. So it's kind of like having a big wedding banquet in the middle of a starving group of refugees, all of this food coming down. And so Bob Breinhoek, who was one of my scientists at MBARI, took ROVs out and did a time series watching the sequence of scavengers that came to feed on this sudden banquet in the ocean. So the crabs that would come in and other animals that would come. But the most unusual animals that fed off this deep sea banquet were a new family, genus, and species of worm in the ocean that grows biogreen roots into the bones of the whale to extract the bone marrow and feed on the bone marrow. So these were very interesting worms. I'll show you a picture here. Here's one of the worms, and this is the part that is sitting above the bone, these sort of white little tentacles moving in the ocean currents. And these are the roots that grow into the bone marrow. And these are fascinating worms because they actually have no mouth and no gut and no digestive system. But in their roots, they have these symbiotic bacteria that actually are able to consume the bone marrow and feed the worm host. So that's the way they eat. What was actually interesting about these for all the women watching this is that every worm that was sampled, and 300 worms were sampled, they were all females. There was never a male worm in the whole group. So the scientists thought, well, gosh, how come they're all female? What happened to the male? Well, they looked very carefully inside the worm, and every female worm had incorporated inside to the trunk of her body hundreds of dwarf males. And these dwarf males were only allowed to develop to the point where they could produce sperm. And then they went into arrested development and spent the rest of their lives just producing sperm for their female hosts. So this is an interesting twist on reproduction. But what was also interesting about these worms is that the 300 worms that were sampled, all female, we did the mitochondrial DNA on them. And the mitochondrial DNA shows how many of them had the same mother. Those 300 worms had 300 different mothers. Now, you have to admit, a whale fall in the bottom of the ocean is pretty unusual. They don't happen all the time. And yet, as soon as those bones were exposed, they were covered with Osedax worms. And so the question is, how did all those worms find that needle in a haystack, that one downed whale, in order to colonize it? One thought is maybe there is some sort of quorum sensing going on in the ocean, like someone ringing the dinner bell and saying, come and get it. And the quorum sensing sends this Osedax larva, which is pretty rare to find in the ocean, and brings them all together. Because otherwise, how can you get the genetic diversity? Alternatively, we looked at whether the density of Osedax larvae in the ocean is so great that the ocean's literally raining Osedax, but that doesn't seem to be the case. So quorum sensing, maybe that's working and helping animals in the ocean find unusual habitat that they can colonize. So let me go on to the next topic, which is assessing and mitigating risk. Because this is something that officers have to do all the time. And in fact, even you students have to do it. You know, what's the risk of, if I only study for my calculus final, I'm going to fail my physics final? And, you know, weighing different choices. So one of the events that I was involved in was the Deepwater Horizon oil spill. And this oil spill was in the year 2010, and it was the largest marine oil spill in U.S. history. It involved unprecedented conditions because the blowout was a mile deep in the Gulf of Mexico, and no one had ever brought a blowout that deep under control. So I was, at the time, in Washington. I was the director of the U.S. Geological Survey. And because of all the experience I had with deep sea intervention at the Monterey Bay Aquarium Research Institute before I went to Washington, the Secretary of the Interior sent me down to BP headquarters to help contain the oil spill, to measure the flow rate of the well, and to try to stop the oil from flowing. So the time series that went on here was one failure after another by BP to try to get this well under control. The explosion happened in late April. They tried putting a cofferdam on it, which is like, it kind of looks like a giant outhouse that you'd put on top of this runaway well to try to stop it. What they underestimated was how much gas was in it. The gas instantly turned to hydrate in the cofferdam and floated it right up to the surface. They couldn't keep it on the bottom. They tried a top kill, where they tried to push enough mud down the runaway well to push the hydrocarbons back into formation. That also failed because they had underestimated the flow rate by, an order of magnitude. And so in early June, they started collecting oil the best they could with a riser and began collecting that at the surface. The collection ramped up to 25,000 barrels per day, but my team estimated that the flow rate was actually more like 50,000 barrels per day. So they were only getting half of all the oil that was spilling into the Gulf. So it was really time to do some more direct intervention to stop it from flowing. So, they were drilling relief wells too, but they were still a month away from killing the well with the relief wells, so cementing it from the bottom. So something more needed to be done. So BP came up with this great idea that they were going to put a capping stack on top of the failed blowout preventer. And this capping stack was basically going to be like a big valve that they put on top of it. They have it open at first, but after they get it seated, then they close the valve and the oil can't come out anymore. So it was a pretty solid plan. However, I was there with a number of geologists from the U.S. Geological Survey, and we raised the prospect that even if the capping stack was successful, it could actually create a worse problem than the one they had. And the reason for that was that during the initial explosion that came up the well, no one knew whether some safety valves that are in the casing for the well had maintained their integrity. And so what you can imagine is this oil is coming out like a hose, and if you put some pinpricks in the hose, the water's probably not going to come out the little pinpricks as long as the end of the hose is open. That's the easy way to get out. But if you suddenly take your hand and put it over the top of the hose so the water can't come out the end anymore, then it's going to start squirting out those side holes. And so the concern was if the oil started getting pushed out the side of the well casing, it could frack its way up to the floor of the Gulf of Mexico, and instead of having one point of the oil coming out, there would be multiple points where oil was escaping, and you would have taken a simple problem and made it a very complex problem. So the scientists came up with, and this wasn't just theoretical. This had actually happened in Santa Barbara. And this is the book jacket from a book called Black Tide, and it talked about how an oil well failed and broached out sideways and created an almost uncontrollable problem. And that was the source of the Santa Barbara oil spill, which led to Earth Day and the entire environmental movement. So my well integrity team, which was a bunch of scientists from the USGS, analyzed the situation and figured out how we could mitigate the potential risk from closing in the well, as BP wanted to do. And what we did was we came up with a simulation of how much time it would take the oil to broach through to the seafloor if it went out these side vents. And what we figured was the key thing to monitor was the pressure on the well after we shut it in. If we shut it in and the pressure was high, then the well had probably retained integrity. Just like if you put your hand on the end of a hose, if it's leaking out elsewhere, you aren't going to feel much pressure. But if you're holding back the whole flow, you're going to feel a lot of pressure. So we decided the pressure would tell us. And if the pressure was up in the range of 8,000 psi, then we were probably okay. If it was really low, then it probably meant that there was major damage to the well. The oil was going elsewhere. It wasn't triggering the pressure sensor on the capping stack, and we'd have to open it up right away before a broach happened. But then there was this no man's land in between. What if the pressure's kind of high, but not really high? That could either mean slow leaks out somewhere, or it might mean that maybe that well has just blown its whole wad, and there's not much left, and that's why the pressure's low. So this was our guide going into putting the capping stack on. So we shut in the well on July 15th, and several hours after shut-in, the pressure started to level off at 6,700 psi, right here in no man's land. So this was in the afternoon of July 15th. The next morning, Steve Chu, who was the Secretary of Energy, and Thad Allen, who was the incident commander from the Coast Guard, were going to meet to decide whether they needed to order BP to open that well up again to prevent broaching. So scientists went back to the drawing board because we decided only science could determine what was going on. And more analysis, as I say, was required. So here's what the well shut-in curve looked like. And here was the simulation from the science team. We simulated both the broach condition and the well that had integrity but just had lost pressure from 87 days of flowing, and came up with a solution that you couldn't get that fast an increase and that steady a pressure from a broach condition. Now, the scientist who did this analysis was a hydrologist, and he's only used to working in metric. All of the data from BP on the reservoir permeability, everything else was all in English units. So he was up all night thinking about that spacecraft that missed Mars because someone did a wrong conversion from English to metric. That's all he thought about all night. But he was pretty sure that this was the right answer. So the next day, when Steve Chu and Thad Allen arrived, we could tell them confidently that the well was going to hold its integrity, and it did. It held its integrity for another month and a half, and well, almost 2 months, until the relief wells finally cemented it at the bottom. So anyway, all right. Now, the next topic I wanted to talk about briefly, I'm really almost done, these last two are really short, are establishing credibility as a valued member of your team. Even if you know all the science, and even if you know how to apply the science to decision making in order to minimize risk, no one is going to pay any attention to you if you don't have credibility. You've got to have credibility with your peers, you've got to have credibility with your superiors, and you have to have credibility with those in your chain of command. So I'm just going to tell you a really quick story of when I arrived at graduate school, I was the only girl there. And there was a lot of concern as to whether I belonged there and whether I could cut it. So it turns out at that time, there was a lot of work going on trying to understand the structure of the Earth beneath the oceans. And to do that, we did seismic refraction profiling, where we used sound sources and either ocean bottom receivers or ocean hydrophones to measure the refracted wave coming up, and from that we could determine what the layering is of the Earth beneath the ocean and the type of lithologies. Well, it turns out at that time, to get really big sound sources, we used explosives because, air guns had not been perfected into large tuned arrays at that time. So my advisor, when I first got to grad school, decided there were only a couple people that were actually had the certification in order to set off the explosives. So he sent me to SEAL team school to train with the Navy SEALs on Coronado and San Clemente Islands because that was the best way to get your certification to do explosive demolition. So the Navy didn't want to take me, but in the end they did. And so I went out there for a summer doing the land work at Coronado and the field work in San Clemente. And what I learned from this was that for the demolitions work, it didn't matter how big and strong you are. All that really mattered was whether you were precise. Because if the instructor told you that he wanted a hole, the size of a bread box in a tank, and you instead blew the thing to smithereens, you would fail just as much as you did if you didn't get the job done. So precision was everything. So I remember at the final exam, my instructor took me to this troop transport, and he said, I want you to blow a hole in the door big enough for me to get my hand through that door. So I built a shape charge and put a detonator on it and set it off. But when the piece came out of the door, I had made a shape charge that actually blew it out in the shape of an ashtray with a seal engraved in the bottom of the ashtray. And of course, all the instructors at that time were ex-Vietnam and they all smoked. And so I handed that to him as a souvenir from the training. And so I graduated first in the class based on that kind of brown nosing. So what the important thing was about this, though, was when I got back to my graduate program, word had gotten around that you don't mess with Marcia, that she is a badass and she knows stuff that you don't want her doing to you. So this was an instant way to get credibility with my group, and from then on I had no problems in graduate school with people thinking that I could cut it and that I belonged. And finally, I just wanted to say a few words about protecting your reputation. So when I was a young assistant professor at MIT, there was all sorts of news going on about President Clinton trying to put together his cabinet. He had nominated several very accomplished women for major posts in his administration. And one by one, they got caught up in a scandal that was known as Nannygate. Because these women, busy working women, had hired household help to help with cleaning and caring for children and things like that, but they had what was called paid them under the table. They didn't declare them as employees, hadn't paid any employment taxes, Social Security taxes, whatever. And so they were in violation of US law, and so they couldn't be hired. I mean, never mind that I'm sure there were many men who had gone through confirmation before that who probably had the same problem with household help, but these women were ruled out. So I decided at that time, I had no intention of ever going to Washington or doing anything with in administration, but I decided your reputation matters. And so I made sure that anyone who worked for me was completely above the board, was a US citizen or had a work permit, and so that nothing could ever come back in my background to cause a problem. And so years later, when I actually got a phone call from the White House asking if I would consider being the director of the USGS, and in particular, whether I thought I could pass the withering background check required for that position, I confidently said yes. Now today there are even more challenges with social media, and that's why I say your social media presence is forever. You can delete a tweet and you know that someone's taken a snapshot of it. So be careful what presence you portray on Facebook or in Twitter or in Snapchat or Instagram or anything like that. it will stay with you for the rest of your life and maybe even in the afterlife. Because a lot of people die today and their Facebook account is still there. Okay, so here's my closing. I'm reading a book right now by Greg Easterbrook called The Blue Age. And he talks about the fact that the last 75 years, since a battle in 1944 in World War II in the Philippines, when the Japanese Navy was defeated, this has been an unprecedented 75 years of peace at sea. There has never been a history since human civilization going that long without a major naval battle. And Greg makes the point in this book that it's because of that 75 years of peace that the Panama Canal's been open, the Suez Canal's been open, the Majorca Straits have been open. It has led to unprecedented economic expansion and prosperity through global trade. And that blue peace from 75 years of no war is because of the U.S. Navy. It's because of U.S. naval superiority. And he also argues in the book that that blue peace could be in peril because other nations have nationalist agendas and they want to build up their navies. And climate change is changing the entire environment that the Navy's been working on and also threatening its facilities. So let me just close by saying, you all are the inheritors of this blue peace. So please take good care of it. And thank you very much.
Good evening, everybody. My name is First Class Mick Zerman. I'll be facilitating some questions. We have time for about a few. Ma'am, thank you very much for your talk this evening. When we learned about geostrophic hills in Commander Gallagher's class, quite honestly, I didn't believe him, so thank you. So if anybody has a question, please feel free to stand up and we'll get them going. We're also matter in the chat, so for anybody viewing online, please send an email to michelson@usna.edu.
I'm at Timberlake, class of '69, and after I left Marine Service, I wound up in OSD, and I was assigned to the White House Tsunami Relief Task Force when it took out most of Indonesia.
Yeah.
The question I have is, it was devastating. The U.S. Navy rallied to the cause. We put an aircraft carrier, Banda Aceh, and the Indonesian people who hated us turned around and loved us. The Navy responded, as did the Air Force. Have we gotten any better on earthquake and tsunami prediction? Do you see a positive trend line there? Because that's one of your risk mitigation factors that science and technology can greatly aid. Thank you.
Yeah. Well, first of all, thank you for your terrific action during that Indonesian earthquake, which was so tragic and so much loss of life. And then also, of course, we had the huge tsunami which caused the Fukushima reactor to melt down, and many people died from that. So in terms of the problem in both Indonesia and Japan was that those were not teletsunamis. Teletsunamis, we've got that problem solved. If we've got, an hour or more, we can get warnings out. But predicting a local tsunami, because the earthquake was right off shore where you are, you can't predict the tsunami unless you predict the earthquake. And right now, we're getting much better at what is called earthquake forecasting. And forecasting means we just say, these areas are more likely to have a big earthquake within the next 15 to 20 years than these areas. And so for earthquake resilience building, that is actually useful to know because you can focus your attention on reinforcing buildings and reinforcing infrastructure in the areas most likely to experience a big earthquake in the near future. For the death toll from tsunamis, actually the best solution right now is still vertical escape, creating vertical routes for people to quickly get above the incoming waves and to make them sturdy enough to withstand the waves. And every time there are great stories that came out of Indonesia and also the Tohoku earthquake of vertical escape that saved lives. But there's just not enough places that have it. Brian Atwater, who's a great seismologist up in the Pacific Northwest, has been really trying to work on tsunami preparations up there, making sure all schools have a vertical route to escape, et cetera, because someday we will have a major earthquake off the Oregon-Washington coast.
Ma'am, we have one that came in from online. Good evening, ma'am. If you were part of the class of 2021 or 2022, what areas of scholarship would have your significant interest? Specifically, what are some fields of research, specifically in field research, that you think have been left untouched or have room for a greater area of scholarship?
Well, that's a really great question. So let me answer it two ways. First of all, there's something to be said about getting in on the ground floor of new fields when they're first getting off, when they're first opening up. It's a time when everything's changing, textbooks are being rewritten. You don't actually have to even read the textbooks because the textbooks are out of date. So there's an advantage getting in on the ground floor. The reason I went into geophysics is because the theory of plate tectonics was written when I was a senior in college. And so by going into geophysics in graduate school, I could get in on the ground floor of a scientific revolution. It would be like going into genetics right after Watson and Crick published the double helix, or into physics right after Einstein writes his special theory of relativity. So right now, I think the most exciting things that are happening are in marine microbiology. So I think that's something that's going to become more and more apparent in its relevance to the Navy. And there's basically, you know, if this room were a drop of water, the exploration we would have to do just to understand all of the viruses, all of the bacteria, and all of the plankton. You know, a plankton would be sort of the size of a big beach ball in this drop, but the others would be tiny, and there would be hundreds of them. So I think that's the exciting thing. But the one thing I will say is that if you continue to learn, you will find over your lifetimes what that it field is going to constantly change. And so you have to keep up with the science so that you can constantly be moving into that it field. So thanks for that question. Okay, so the question for those of you who may not have heard is, so many of our technical advances have come in times of war. So what do we do in a time of peace? How do we keep up? So let me just give you a little time horizon over my career. So I went into oceanography and marine geophysics during the Cold War. The Cold War was actually almost better than a hot war. And the reason is very few people were dying, you know, maybe a spy here or there, but basically our troops weren't dying, but yet we knew we had a competitor. That competitor was the Soviet Union, and we had to stay up with them. And so there was this, there was funding for research, there was funding for 6.1, 6.2, 6.3, 6.4 projects, because it was important to get basic research into operations, because we never knew when tempers would flare. After the fall of the Soviet Union, I almost felt like, projects were evaporating, there wasn't the urgency, because there wasn't that competitor that we had to keep up with. There was too much relaxation. Well, now the concern is obviously with China. China is building up its Navy. It's got the Belt and Road Initiative, which is put forward as economic expansion, but basically is trying to improve China's connectivity with the rest of the world. I forget what the statistics were, but out of the top 10 ports in the world, the first 4 of them are all in China in terms of trade. So, basically, China's becoming a very seafaring nation, and we have to keep up. So I think it's that competition that keeps it at our best. And it's the same in anything. If you're a sprinter, if you don't have someone good to run against, you're not going to be any good.
I think we might have time for one last quick question.
Okay.
Up top there.
Good evening, man. Shipman First Class 1. I found your talk about quorum sensing, really cool. My question is, if we do find a gene that expresses the quorum sensing, how would we deploy, I would assume we put it in another microorganism and have it create that protein or whatever. How would we deploy such a capability without interrupting or outcompeting natural organisms?
Yeah. Okay, so right now the quorum sensing is in bacteria, but let's suppose we could put it in zooplankton. Now we've increased the size by immensely. So I'm not going to exactly predict what might be the limits of quorum sensing, but it's just sort of like right now we feel constrained by our senses. We have our eyes, we have our nose, we have our mouth, we have touch, we have hearing. But those are all the senses we have. But quorum sensing, we can't do quorum sensing. But what if other organisms in the ocean could, and it's something it's sort of like, I'll tell you that every time I've been involved in a new discovery in the ocean, it's always been because we created a new tool that was a new eye or a new ear or a new sniffer or a new way to touch the oceans. And now we're talking about having an entirely different sense that we never dreamed of, that it even existed. I mean, that would be pretty exciting. Thank you for these great questions. You've been really a wonderful audience, so thank you all very much. Sorry, I left too soon. I guess I get gifts.
This is gift-giving time. As Dean Phillips and Captain Wolper stated earlier, we are so proud as the class of 1969 to have been doing this for 40 years. You are the 41st speaker. The list, I hope you've seen, of your predecessors. I've been at each of these for 40 years, many of my classmates as well. We apologize that this is not an incredibly packed auditorium as it usually is, with as many midshipmen as we can fit in here. But for our 10th anniversary, we decided we would create this Michelson Lecture 40 years ago. And as you see in your program, the incredible scientists and Nobel Laureates that have presented, you are among the best presenters that I've ever seen here. I appreciate it. Your talk was understandable. It was appreciated. And I'm sorry there weren't more people actually here. We have a virtual audience that's enjoying it. So we're going to give you a couple of things now. On behalf of the United States Naval Academy, first of all, the oceanography and the School of Mathematics and Science has done a fantastic job, as you pointed out, and the dean has pointed out. This is one of the best prepared evenings we've had, so thank you to the professors, the staff, the midshipmen in the oceanography area. So they've actually given me something to say so I don't forget anything, so hopefully I'll just read it. On behalf of my Naval Academy class of 1969, my classmates, all of the alumni of the Naval Academy, and the Naval Academy School of Math and Science, I'd like to present you first with 3 tokens of appreciation. First, as a military tradition, you may be aware there's a challenge coin, commemorative coin. This is our class of 1969 commemorative coin. Every one of the predecessor speakers has received a coin like this, just like we're giving to you. We're going to, normally you shake hands. I'm not going to ask you to do that. Okay, I'm going to give it to you there. So that's the first gift from us to you. A little asterisk here. A couple of years ago, one of our speakers wonderfully brought their Nobel Prize laureate with them, okay, which looks like a little frisbee, which first time any of us had seen it. And he was nice enough to bring it up. And when I gave him the coin, he gave me his Nobel Prize to me to give back to my class, which we then exchanged back again a little bit later, okay? But he said he was going to put it right next to his Nobel Prize, okay? So you're small group of people who we have given this to. So thank you very much. That's from our class of 1969 and all of the alumni of the Naval Academy. Secondly, Grace Santella, a midshipman, first class here. She's going to help me with the next 2 presentations. Grace, you give it to the doctor, okay? Dr. McNutt. This is a ship's clock from the School of Math and Science. That's the first.
It's beautiful.
There is a ship's clock in there. Okay. It's a little one, I guess. I don't know.
No, it's big.
Is it big? Okay, good. All right, good. The third gift, and the second one from the Naval Academy, is water from the oceans of the world, collected by graduates of the Oceanography Department who are currently sailing aboard our United States Navy warships around the world.
That's fabulous.
There's water from the 7 seas.
Oh, my goodness.
Dr. McNutt, we sincerely appreciate the time you've taken to visit with us, this excellent presentation that you've given us. We've thoroughly enjoyed the presentation. And now we're going to invite everybody, led by Dr. McNutt, to join us outside of Mahan Hall for a reception. Thank you all. Thank you very much.